different way than the last one we had. This one is intended to work against the specialization that we have, right? I was told in university that Gauss was the last physicist to have a good grasp also of many other sciences, and now you often find it's very hard to understand what the Nobel Prize in Physics was about if it doesn't happen to fall in your particular field. So we have Professor Alfredo Segura with us today, who works in the field that these gentlemen work as well, or at least close enough that he could explain it to us. And I hope that after we're done today, we have a better understanding of what this Nobel Prize was about. We know it's topology, so that's something about donuts and pretzels, and that has some applications in solid state physics. And how we got there, I don't know. And I hope after an hour today we will. Thanks. Go.
Okay, thank you very much. Well, I thank the organizers of the colloquium for this opportunity to discuss solid state physics with physicists from other fields. Okay, you all know that the Nobel Prize of 2016 was awarded to Knowles, Kosterlitz, and Haldane for theoretical discoveries of topological phase transition and topological phases of matter. So there are two different fields, let's say. Well, you see how half of the prize was awarded to Knowles because he turned out to work in both of the parts. Say first, in topological phase transition, of course, they discovered a new type of phase transition, not related at all with the traditional description of phase transition in terms of symmetry breaking, order parameters, etc. And then he worked later on developing the first interpretation of quantum Hall effect and showing that it was the first topological quantum number in solid state physics. So when the speaker of the academy tries to explain with which the Nobel Prize was related, he started talking about these topological differences in some kind of bodies, and we can see if we stay in the foundation region, we can see clearly that there is a different topological difference between it could be a donut or a kind of king cake and Easter cake. Okay, so the point is that this difference is very easy to understand, but it is not so easy to go to the point of how these topological ideas apply to solids, because they apply in spaces that are not at all the ordinary space. So the insight this kind of comparison can put forward is not very important. So we have to go through a series of steps, and the idea is that at least when you've finished this talk, you will be able at least to see the paths to go to a better understanding of these ideas. So we start with the idea of symmetry. Most of the development of physics has been based in ideas of symmetry-based ideas, through the Noether's theorem. Then we introduce very basic topological ideas, and we'll see how they apply to the electronic structure of solids. We have to introduce the concept, the idea of Doris phase and Doris curvature, because this is the one that plays the role of Gauss curvature in the Hilbert space. Then we'll describe the first topological system that was discovered, the quantum Hall effect system. We will simply mention some further development, and then we'll go to the area of topological phase transition. So to start with symmetry, since Emily Noether formulated her famous theorem, which the conservation states that the conservation of physical quantities like linear momentum, the angular momentum of the energy, are related to very general symmetries of space and time. All of us are more or less familiar with this, and we can safely say that symmetry-oriented, symmetry-inspired reasoning is probably the most fruitful kind of reasoning that has been developed in physics. So how can we go to a different kind of reasoning? How can we introduce topology and solid-state physics? But topology, the birth date of topology is more or less agreed that it was the famous problem of 7 bridges that was proposed by the Council of Königsberg. They were very proud of their city, and they wanted to make it known, and they imagined this problem. It was possible to find the path through the bridges of the city in such a way that you would, from one point of the city, you could go through all the bridges one time only per grid, and go back to the same point. But the point is that Euler immediately recognized that it was not a matter of the size of the, let's say, the land masses, but simply the disposition, the general disposition. So he realized that it wasn't really a topological problem. He invented the graph theory by reducing the ground masses to points and the bridges to lines. He realized that to do the complete walk, you had to enter and exit every ground mass, and he realized immediately that you needed an even number of bridges per land mass to have to complete the path without going twice through a single bridge. So obviously you see that every one of them has at least odd number of bridges. There are a number of bridges per ground mass. It means that the problem cannot be solved. There is no path, such a path. So we also owe to Euler's what is called the Euler's characteristics of a convex polyhedron. Everyone knows from geometry that the number of faces plus the number of vertices equals the number of edges plus 2. This is a general feature of a convex polyhedron. And if we can define the Euler characteristics by this difference between the number of faces plus the number of vertices minus the number of edges, it turns out to be 2 for all convex polyhedron. It means that this is a topological invariant. If we put some kind of hole in the polyhedron, not convex but some kind of concave part in the polyhedron, you can simply by adding edges and faces and vertices that for this kind of polyhedron you're going to have a Euler's characteristic equals to 0. You increase the number of holes, it is going to change by -2, -4, minus. So this is clearly an invariant of the polyhedron. So we can deform a polyhedron and convert a cube into a sphere, and this kind of polyhedral toroid into a torus. Does it conserve some kind of topological invariant? Well, it was introduced by Gauss, this idea of the Gauss curvature, and he realized that the integral of the Gauss curvature, that is the inverse of the problem of 2 main curvature radii, when you integrate over the whole surface, it leads to a number that we can identify to the Euler characteristic. We're going to see how. Well, this is obvious for a sphere. It's a little like the Gauss is related to the Gauss theorem. We see that indeed we find 2, like in a convex polyhedron. If we go to a torus, we find 0. But the point is, how can we define the curvature of something that is flat, polyhedron? This is also done by something called Gauss mapping of a vertex by, if we take a corner of a vertex, we trace, we put some plane perpendicular to each of the line converging in the vertex, and then we can measure the surface subtended by 3 planes over the sphere of radius unit. It gives us the contribution of the vertex to the curvature. So all the curvature, according to this Gauss mapping of the curvature of the polyhedron, concentrates in the vertices, such a way that in this Gauss mapping a cube is mapped into the unit radius sphere, each vertex corresponding to 1/8 of the total curvature. So this is, you can find in topology books a rigorous demonstration of this in such a way that we can safely say that the Euler characteristic is a topological invariant of any closed surface. We can even define what is called the genus of an object, like this, which is corresponding to the number of holes. All these objects have genus 0, no holes. All these other genus 1, one hole, and those 2 holes, genus 2. So how could we go a little further, and how can this kind of reasoning apply to physics? So how to go from this parallel to this kind of symmetry-based reasoning that still is extremely fruitful, to go to a topological reasoning? How can we find an equivalent of the Gauss-Bonnet theorem with topological invariant in a solid? And which curvature does it refer this possible theorem, and in which space? So now I'm going to try to give some little introduction to solid state concept, spaces and curves that can be found in solid state physics. Starting by one of the most simple and basic and most fruitful ideas, which is the Fermi sphere. The free electron gas is the simplest quantum system with wave plane as wave function, a plane wave as wave function, and an energy that is just kinetic energy depending on the square of the wave vector. So we can apply boundary condition. We see be it infinite potential at the surface. We have stationary waves of the classical cyclic condition we impose in solid state physics, which leads to propagating wave. Anyway, in both cases, the allowed values of k are uniformly distributed in the k space, what we found can easily find from this idea of stationary waves, we can find the density of allowed state in the k here, and then by applying the Pauli exclusion principle, we can fill the states, starting from the lowest energy state to the highest energy state. When all the electrons available are occupying their states, we have what is called the Fermi surface, the Fermi sphere, whose radius and energy depend only on the electron concentration. This model was proposed for investigating the properties of metals, but it is unbelievably powerful, and it is being used also for astrophysical objects like white dwarf work perfectly with white dwarfs, so for the neutron stars, and it is able to predict the equation of state, the mass at which dwarf state is going to collapse into a neutron star. Is incredibly powerful model. And then we see how we have a first surface in the K space. So then, because the Nobel Prize is related to the two-dimensional system, let's introduce what is the two-dimensional electron system. This is an artificial structure that is done by confining electrons on a surface by applying in a metal oxide or insulator semiconductor. We apply a tension that attracts the electron and create in this way with a high potential of the oxide and the potential of the electric field. We create a quantum well that confines the electrons on the surface and let them to move freely along the plane. So we have exactly a two-dimensional Fermi gas. We can do the same kind of reasoning, impose the boundary condition, the same kind of dispersion, same kind of energy-momentum relation, and then the allowance states are uniformly distributed, and we fill, in this case, the Fermi circle, and calculate the Fermi wave vector and the Fermi energy. In this case, it applies only to solid-state devices like heterojunction, most devices with electron concentration not very high, and with Fermi level, Fermi energies that are in the order of 1 to 100 milli-electron volts. This is typical. They are typical solid-state devices. So what happens now? What happens in solid? In solid, things change because we have the Hamiltonian is not invariant for arbitrary translation, only for a discrete set of translation that belong to what we call the Bravais lattice, multiples of the unit cell parameter. Okay, so not only this, so the momentum, the ordinary momentum is not conserved. The quantity is conserved is called the quasi-momentum that can be assimilated to the ordinary momentum for long wavelengths. And the other important feature of a solid is that there is, for any kind of wave we can imagine in the solid, be it solid lattice vibration, wave, electron wave functions, there is a minimum wavelength. We need at least 2 atoms to create a wave. So this minimum wavelength establishes a limit to the maximum momentum, maximum value of the momentum. So this Bloch in the early 30s applied quantum mechanics to this problem of electron in a periodic potential, and found that the kind of wave functions that the kind of stationary states are called Bloch functions that are periodic function multiplied by phase factor plane wave. Okay? We can construct this kind of state by combining atomic orbital with atomic states with phase factor. Okay? And the important thing is that the existence of a maximum for the wave vector means that all different states are contained between minus pi over a and plus pi over a, which is called the first Riemann zone. All the states, the rest of them, are equivalent to that one, and we have this kind of periodicity in the reciprocal space. So it means that the solid is something very special. We are going to have the states are going to be distributed in bands. The quasi-momentum is nearly quasi-continuum, and we have bands separated by forbidden bands in which there are no electronic state available. We can assimilate in the maxima and minima. We can describe the solid electron as if they were free electrons with different mass. It's called the effective mass in the solid, in the band. But they are clearly very different things, And the main difference is the fact that while in the free electron we have an infinite, there is no limit, there is no bound in principle to the wave vector. In the solids there is a limit. Not only that, but the states, because the states between the border of the square Brillouin zone, where we have all the available states, all the possible different states, are identical states. It means that the topology of this square is not trivial. In fact, this edge is completely equivalent to this one. It can be closed this way, and this edge is equivalent to this one. And the topology of this any first Brillouin zone is equivalent to a torus. So this is the first difference, main enormous difference between free electrons in the free space and electrons in the solid. So depending on the number of electrons that are occupied, we have what the famous classification of one of the main results of the band theory developed by Bloch and other researchers is the fact that they could explain the insulating or conducting character of solids. The insulators are solid in which all the states of one band are occupied, and there is a large gap between the following band of unoccupied states, so there are no low energy excitations. While in metal, we have excitations even at zero energy, because there are available states for any low energy excitation to occur in the metal. So there's a big difference between metals and semiconductors. This is one of the keys of this kind of topological reasoning. Because when we look at the difference between many kinds of insulators, we see that it is possible by some kind of adiabatical process to transform the electronic structure of one insulator into the electronic structure of the other. A paradigmatic example would be the case of gallium arsenide. Gallium arsenide can be its electronic structure simply by compressing gallium arsenide, by changing slightly, applying the hydrostatic pressure. We can transform its electronic structure into the electronic structure of aluminum arsenide. But they are said to be topologically equivalent insulators. So for insulators, there is very large kind of insulators, depending on their provided the gap is finite and there are no vanishing energy excitation. We have insulators like silicon with one gap of 1 eV, atomic solid, an atomic solid like solid argon under pressure that has a gap of 10 eV, or the vacuum in quantum electrodynamics, that is an insulator with a gap of 1 mega electron per the so they are all topologically equivalent, and when we put together two topologically equivalent insulators, that nothing happens in the interface. It's said to be a trivial interface. There can be some exchange of electrons, there could be some barrier, but there is nothing, let's say, topologically protected, because the junction is trivial. What happens if we have a different kind of solid? Kind of solid that, let's say, we activate some kind of interaction. That could be the spin-orbit coupling. Spin-orbit coupling in a solid. You know that you can go from a very low spin orbit, depends on the atomic number, it's a relativistic effect, and we have very low spin orbit coupling for light elements and very high spin orbit coupling with heavy elements. The largest number stable element is bismuth. All the other elements are unstable, the nuclei are unstable, and this is the one in which the spin orbit coupling is the largest. So sometimes when we introduce heavy elements in an insulator, we see how, because of this spin orbit interaction, there is kind of band superposition. The bands belong to have different symmetry, they don't meet. This will be overlapping metal. But if the bands belong to the same symmetry, have the same symmetry, there is a mixing and the opening of a gap. These two insulators cannot be topologically equivalent because in the process of going from one to the other, necessarily we go through a metal. So it means that the interface between those insulators, there's going to be a point in which there will be some low energy excitation. So the interface between two topologically non-equivalent insulators, there should happen something necessarily that will be in order to fulfill the condition of the continuity or the wave function and the probability current. A system must exist there to fulfill these conditions that is topologically exists there because of the topological difference and is said to be topologically protected. We're going to see one clear example. So, in which space can we distinguish between what we would call donut or orange insulators? Well, the electronic structure of a solid is described by finding for each value of the wave vector inside the Brillouin zone that it's not trivial, it's torus. We make it correspond. We will have for each band a state, an element of the Hilbert space of the system. Okay? So this is like defining a field in some way, but if you want to go to the rigorous form, you must go to some topology book like the Nakahara, in which you will find what is called a fiber bounded. This is rigorously defined to the idea of a fiber bounded. Well, the definition is nearly one page in the Nakahara book, so I'm not going to go much further with this idea. How can we find a simple system to describe these differences in topology? The electronic system, one-dimensional electronic system, can be very complex, and they are the simplest thing we can imagine. So in one dimension, the Brillouin zone is going to be a segment that is equivalent to topologically equivalent to a circle, because these two states are identical. Then let's start with a system like, let's say, trans-polyacetylene. That is a system in which the time reversal symmetry is respected. It is even under time reversal, and because of this, the Kramer's theorem holds, and this have this identity between the states for different sign k vectors. So this, we see the fiber bundle associated to this electronic system. We see that it is topologically equivalent to a cylinder. It is said to be a trivial insulator or a trivial system. But if we go to a system like a chain, ferromagnetic chain of spin, linear ferromagnetic chain, we see that in this case the time reversal is not fulfilled, and we have this relationship related to the fact to the properties, the symmetry properties of the spin versus the rotations. Okay? So it means that the fiber bundle of this system is going to be equivalent, topologically equivalent to a Moebius strip, and then it's not going to be trivial. So this is the line of reasoning that lets us introduce this topological difference. Now let's go to magnetic field, because the system we are going to study is the the quantum Hall effect. The first this is to treat the problem of the electron in the magnetic field was now. Well, classically we know that electrons in the magnetic field describe circle orbits, and with a constant frequency, provided the electron is not relativistic, and what this frequency is called the cyclotron frequency, in reference to the first kind of accelerators, the cyclotrons. So what Landau did was to show that in a magnetic field, using it's called the Landau gauge, he showed that the states of the electron in the magnetic field are equivalent, can be decomposed in a harmonic oscillator with a cyclotron frequency as quantum energy, and then a continuous sort of state corresponding to the movement of the electron along the magnetic field. So it does, what it does is when we apply a magnetic field to a three-dimensional solid, we have densities of a state that are infinite for each, the beginning of each Landau level, but also we have the energy corresponding to the free movement of the free electrons along the axis of the field. Well, it means that we have a Fermi level somewhere, even if we apply, if it is a half field band, there will be a Fermi level. Even if we apply a magnetic field, it is going to be a conductor, it's going to be a metal. So applying a magnetic field doesn't change the nature of the material, if the material is 3D. But if the material is two-dimensional, two-dimensional free electrons, because electrons are already confined, we apply a magnetic field perpendicular to the system, the electrons cannot move freely along the field, they are already confined. So it means that if initially we have a metal, when we apply the magnetic field, it's going to become an insulator. Okay, so the presence of magnetic field changes the topology of this system. This system clearly is a special system because by applying a magnetic field, we have changed the nature from metal to insulator. So now let's refer to the another concept that we will need to describe the quantum Hall effect is the concept of geometric phase or Lorentz phase. So we know that in a system, the stationary state evolves in time following what we call the dynamic phase factor that depends only on the energy of the stationary state. What Berry did was to imagine what happens if the system, the state of the system depends on a given series or set of parameters. And imagine what happens if we make the system to adiabatically describe a closed circuit along in this space of parameters. Okay? What he discovered is that on top of the dynamical phase is going to be what he calls a geometric phase factor that depends only on the circuit traveled. And he found the analytical form of this phase factor. He introduced this vector in this parameter space that is called the Berry connection, this state. And by applying some generalized form of the Gauss theorem, he discovered, or he introduced the idea of Berry's curvature, and showed that the phase change is related to the total curvature of the Berry's curvature of the state. You can assimilate this to the Gauss theorem in some way. Huh? The Gauss theorem in topology. So this idea has been previously used, especially in optics. Panchavatna has developed the idea of a geometric phase depending only on the path of the beams through a series of optical elements. In this case, in the Poincare sphere of polarization. But there are simpler. We are going to see two very simple examples of geometric phase. The Foucault's pendulum, what everyone knows, have probably explained in mechanics how the rotation of the plane of oscillation of the pendulum is related to the movement of the Earth, and by introducing fictitious inertial forces, we can find a very exact expression for the dependence of the rotation angle of the plane of oscillation as a function of latitude. The idea that it doesn't really depend on it depends on the product of the frequency multiplied by the time. So it means that if we increase the frequency by 2 and the time by 2, divide the time by 2, we are going to have the same result. So this suggests that this is a geometric phase problem and related to the parallel transport on a surface. If we are on a plane surface and we define a figure of geodesics, it's a triangle, the rules of parallel transport means that we keep the angle through a geodesic, the angle that the vector forms with the geodesic, in this case, is a straight line. We go through a circuit and the phase, the orientation of the vector doesn't change. But if we are on a sphere and we construct with the geodesics of the sphere, we construct this spheric triangle, we can immediately see that when we translate the vector applying the rules of parallel transport, there's going to be a change of the angle. Okay, there's going to be a phase change in the vector simply by the fact of translating it parallel to the geodesics. Okay, so what happens with the pendulum? Even if in the planet with no rotation, if we took a pendulum along the equator, then along this line and then back, we will have, by applying the rules of parallel rotation, you see that there will be a change of phase by pi over 2. So this is clear that the effect of the Foucault's pendulum is simply parallel translation through a non-equatorial line. It doesn't happen if any maximum circle we travel, there will be no change in the phase. But if we go through paths involving changes to another geodesic, there will always be a change of phase proportional to the area of the inside the circuit. Okay? For the quantum example, we have the Aronoff effect. We imagine free electron in a box around the solenoid, a very tight solenoid with letting not being sure that the magnetic field is only inside the solenoid. And what we can find, we know that the wave functions are plane waves, so we can use this wave function. We can define them as a function of a parameter like the origin of the coordinates in the box, and we can calculate the various connection in a very easy form. It has a very easy form. It's simply by applying the gradient of the wave function with respect to the parameter, we have simply this generalized momentum, including also the electromagnetic momentum. Okay, so we can calculate the geometric phase, and we see the geometric phase depends on the magnetic flux that the circuits subtend. This is exactly what happens in an Aronoff effect experiment, in which the experimenter can see how even if the electrons go through a region in which there is no magnetic field, he observe a change in the phase that corresponds exactly to the geometric phase. For P, we change we apply no field or field. We can see that in the two slits experiment there is a change in the phase that corresponds exactly to the geometric phase. These are two examples. In the solid, the very natural way of defining the very phase is through the parameter is the wave vector, and this is so because when we calculate properties in a solid, normally we do this through integrals of some of the operator of some physical quantity, the current, the electric dipole, and we calculate the average. We calculate an integral extended over all the states of the solid, so we have to do integrals into the first previous zone. So we calculate in this way the very space of a band, and by applying the definition of the Berry connection, we find this expression for the Berry connection, which is this vector, and for the Berry's curvature, that is this other is the rotational of the in the K space of the Berry connection. We can see how this can be related to calculation of properties. You can see here the gradient in the key space is either the operator of the position in the K representation or the operator of the speed or the velocity in the R representation. You see how the Berry connection naturally appears in problems of polarization or conductivity. This is the idea behind the development of Dobles and Costellet. Dobles and the other group of collaborators. So, what is the Hall effect? The classical Hall effect is what everyone has done an experiment in a student lab. We have a sample, there is a current, we apply a magnetic field perpendicular to the current, and because of the magnetic field, electrons are diverted to the edges of the sample, and when they accumulate, because there is no continuity, accumulate, they create a field. The electric field is called the Hall field. This Hall field creates a force on the electron that compensates the magnetic force. Then we have, once the equilibrium is attained, we have the same current flowing along the same along the sample, and an extra field perpendicular to the sample. And this the condition is fulfilled when both forces are equal. So we can calculate what is called the Hall resistance that depends on the magnetic field and the dimensions of the concentration, electron concentration of the sample. So we can say that in this case there is a kind of resistivity tensor in which the diagonal element doesn't change, and there is a cross term that correspond to the Hall resistance. So if we impose some kind of boundary condition, there are no, we put a voltmeter with infinite impedance here, there is no flow, so the current goes only in this direction, and gives us the condition as a function of the field, the resistance, the linear, the diagonal resistance is constant, and the Hall resistance increases with the magnetic field. Okay. So what happened in 80 when von Cleveland and his group discovered the quantum Hall effect? Well, for the low energy, you can see that everything goes the same that is predicted by classical Hall effect. But immediately we see some kind of strong oscillation to appear, and the Hall resistance start having steps, and these steps correspond exactly to a resistance that is called the Von-Clifton resistance. And this is so well defined. All the trials to measure with high precision this resistance have resulted in showing that it is defined to an error of 2 to the minus 10th. It means that it's really this is the reason why it is on the way of being introduced as one of the constant that is going to be in the future international system of units. So what is the origin of this extraordinary precision in systems that can be full of defects? I mean, this kind of samples, even they are very good, they high electromobility, they have a lot of defects. So how can we obtain this kind of results? So the idea is how do electrons in a solid with a magnetic field behave? This is a very complex problem. There is no solution, and there have been only, let's say, partial solution of the problem, because there is the mixture of the periodicity of the solid with the periodicity of the field induced by the cyclotron resonance, the cyclotron orbits. They don't go necessarily together. So this was first treated by Douglas Hofstadter for a simple case by assuming a band with a very simple dependence on the k vector, the simplest form of band, and then he found that this kind of band treated with a series of hypotheses, he could find the complete spectrum of the state by introducing some specific values of the magnetic field, measuring the field in units of the quantum field over the area of the unit cell. Okay? So this is a very famous fractal. It's called fractal butterflies. Hofstadter left the physics, and he's now a philosopher. You may know him because he has written very famous philosophy books. So what did Nobel and his collaborators? They solved exactly the same problem. They showed they did in a more general case, and they obtained the full energy spectrum of wave functions. They applied the linear response theory to obtain the whole resistance in the Q-Mos, what is called the Q-Mos formula, and they found this kind of. I told you that every time we treat problems with currents or polarization, we are going to find something that is related to the Berry's curvature, and indeed they showed how the contribution of each Lambda level to the conductivity was related to the Berry's curvature, and when the Lambda level is full, it corresponds exactly to what is called a Chern number. It is one when only the first Lambda level is occupied at very high magnetic fields, and exactly to the quantization of the energy, sorry, of the conductivity. Okay, so how can we put it in a more say intuitive form? Well, we have seen that the quantum Hall system is a non-trivial topological has non-trivial topology, which means that there must be edge states to fulfill the condition between this special topology insulator and vacuum that is a trivial insulator. And this low energy excitation system is created by the electrons that do not complete the orbit, the cyclotron orbit, and they flow along the edge in a carrier system, with electrons flowing always in the same direction, because they flow always in the same direction. There is no scattering. This is a dissipation-less system. So near to the Fermi surface, the speed is going to have always the same sign, and the dispersion, the energy-momentum relationship of this system is going to be linear. So it led us to see what's going to happen if we change the Fermi level. We can calculate the increase in the number of the density of electrons up and down. This is in the absence of a current. If we apply a current, if we make a current circulate, what is going to happen is that there's going to be, you remember that there is no dissipation, so in this direction the potential difference is zero. There is only a potential difference due to the Hall effect, and this leads to a difference in the Fermi level. The difference in the Fermi level is exactly the amount of the Hall effect voltage, and we can calculate from this Hall effect voltage how the density is going to change between the two lines, the up line and the top line and the bottom line. Okay, so we can calculate the density. The density is related to the increase of the K vector. We can relate to the Hall effect by calculating which increase of the K vector, the difference between the K vector in the top and bottom lines, and from there we can calculate following this reasoning, we can calculate the relationship between the intensity located here and the voltage, which is exactly the von Klitzen resistance. And so later on, Haldane showed, he predicted that this kind of resistance quantization could be observed in this in 1988 through a kind of trick. Imagine this kind of the really theoretical trick in a network like graphene. He imagined that between the two of second neighbors, he introduced a term of interaction between the two second neighbors that are equivalent to the level of graphene, and this term acts as a kind of local magnetic field and breaks the time reversal symmetry. So this was a theoretical prediction, but many years later, there was those experimentals, Cheng and workers, that showed that this was the case by taking this semiconductor doped with chromium. They showed that in a MOS device, two-dimensional system made with this material doped with chromium, they observed that the resistance was quantized as predicted by Haldane. So this kind of reasoning has led lately to an enormous field of work. It's called all the topological insulators and materials. The explosion, let's say, started in 2010, and there have been a lot of systems started. They are called spin control effect, topological insulator, in which different systems are observed, like the Dirac cones on the surfaces that are topologically protected states with electrons that behave exactly as in graphene, with a linear energy momentum relationship. lately, one of the last discoveries is the prediction by of what one called vile semimetal that are material with bulk Dirac cones that we have as the old prediction of the vile fragments. So this field is really boiling. There are hundreds of publications every year, and well, some people say that probably in solid state physics, in the next future there is another Nobel Prize to the field. Probably will be one of those developments because they are really spectacular, related to the fine tuning, let's say, that the physics solid state theories have reached. They are able, with these new tools, they are able to reproduce very, very finely predict very special properties of the solids. So let's go to finish with some. Sorry, I'm little late, but this is much simpler. But the idea of the topology of phase transition is related in ordinary transitions. We have a change of symmetry, and there is another parameter. So in paramagnetism, we have a complete isotropy of the solid. The spin can be oriented in the direction of the space, and through the transition, we have to select a specific direction. There is a breaking of the isotropy of the rotation symmetry. This is the kind of the concept we use for this three-dimensional transition. But well, in the 30s, I suggested that in 2 dimensions, the oscillations, the fluctuations would be too high to have symmetry breaking. This was transformed into a theorem by Mervyn Gardner and Hohenberg in 1968, based on the idea of the Goldstone theorem that says that when we break the symmetry, there is a kind of rigidity. This rigidity is going to create some low energy excitations. These low energy excitations are called the Goldstone bosons. We're going to see some examples. So in low dimensional solids, 2D and 1D, there will be no transition because the fluctuation generated by the vanishing energy Goldstone bosons will be so high that it will be impossible to have any phase transition. So this is the example of which symmetry will break in the liquid solid, the continuous oscillation, and the interatomic distance is the other parameter that gives rise to these phonons that are very low energy excitation. The same way we have magnons, or in the normal superfluid transition we have what is called the third sound. This is temperature pulse that propagates as a wave with a given speed and not in diffusion. So what Kosterlitz and Gomez did was to change the perspective. See, why don't we look at topological defects that we know that exist in system, in the solid system? So the idea is based on the difference between what we call a point defect, like it's a spatial vacancy, Frankel pair. These are defects that affect the neighborhood, but the solid remains the same outside, beyond some interatomic distances. On the contrary, when we have a dislocation is, for instance, when we take one of the planes, the crystal readjusts. This is a very small change in the distance. We have millions and millions of crystal planes. If we take one, it is not macroscopically it is not noticed. But this defect affects the whole solid. It's impossible. You go along as further as you want beyond the defect, and you will notice that this defect exists. Here you do a path, you define a path of steps in one direction, or perpendicular direction, and going back to the same to the same atom, you cannot notice that there is a defect at a given distance. Here, when you go do the same kind of path around the edge dislocation, you cannot arrive to the same point, and you will arrive to a different point, so you can define what is called a barrier vector, the barrier vector, which is a topological invariant. The screw dislocation is when you, along an axis, imagine you cut a book from the center, and then you stick a page to the following page. The same, when you do the path, you will have a difference that is from the beginning to the end. There will be a step corresponding to the number of planes that have been 40. So these are topological defects, clearly different from the point defect. The topological defect affects the whole structure of the solid. So they started thinking that in a system like spin, or a system of spins, or a system of vortices in a superconductor, you can have vortices of spins or vortices of superfluid. Vortices of superfluid. We know that these vortices transport unit quantum of angular momentum, and so how do these vortices behave in those 2D systems? What they found, they did parallelism between the vortices and the electrostatics in 2 dimensions. In 2 dimensions, we know that the potential between the potential of a charge depends in 1 over the radius, which means that this is the force, and the potential then depends logarithmically, which means that the energy associated to this kind of charge doesn't converge. It has the logarithmic divergence. You can it doesn't. The larger the sample, the larger the energy. So it would be impossible to excite this kind of thing. The energy of this vortex would be related to the size of the sample and the core, the size of the core of the vortex core. So nevertheless, if we do the same way as in electrostatic, the dipole in 2 dimensions would have well-defined energy, the reason that vortex and the vortex couples would have what they call the topological charge 0. So they could be excited because they have a zero energy, finite energy excitation. Then in a vortex we have non-zero topological charge with infinite energy, cannot be excited, but the couple vortex anti-vortex is not topological. You can see how if we go further, the spins or the speed of the liquid is going to disappear. It's going to go to the stationary situation, the non-perturbed situation. So it has an energy that is not infinite. So they reason that at some point, low temperature, pairs of vortex anti-vortex can be excited, and then at some temperature they could be separated, and in this case there will be a big effect on the state of the system. So they calculated the free energy, and they saw how even if the energy of the vortex is very large, the term due to the entropy would make at some temperature the free energy to change sign, and the system, this kind of separation, to become stable. At this point, when the couple of vortex and anti-vortex are split, there will be a big change in the system, and the number of superconductor, superfluid atoms would decrease, and it could be observed some kind of measurement. This This is what, so they determine the temperature at which it occurs, depending on the interaction energy, and some experimenters have shown this by very sophisticated measurement. They studied this researcher, Bishop and co-workers in 78. What they did was to study the changes in the phase and frequency of a torsion pendulum made by layers of Mylar introduced in a superfluid. So it creates 2D layers of superfluid, and in these 2 layers of superfluid, 2D layers of superfluid, we will have this excitation of vortex, and depending on the temperature, at some point there will be this couples vortex and the vortex will separate, and this will rise to a transition, because the independent vortices will destroy a part of the superconductor, the superfluid state, because of this very high energy. So they studied this experimentally, and they showed that depending on the density determined by the distance between the minor plates, they could identify the temperature of transition, and from constructed the prediction by Kosterev and Dores. It has been used, this kind of theory has been shown in very different kinds of systems, like disorder superconductor thin films, artificial 2D networks or superconducting tower junctions, melting into dimension, etc. So I hope I have given you some ideas that if you are interested in the subject, you can maybe go a little further. There is a list of bibliography I can introduce also in this presentation if you are interested, and if not, it is the list of bibliographies is in the web page of the School of Physics. I thank you very much for your attention. Sorry for the length of the duration of the talk, but
yeah, I think it was very interesting. 2 questions?
Sorry, maybe it's a bit technical question, but I am a bit confused about the formula that you showed to calculate the Chernow number. You integrate over Kx and Ky. Okay? But in presence of a magnetic field, then you will, the question is whether it makes sense to use the same quasi-momentum as in the field-free case.
it's like here.
I mean, if you include the magnetic field, then you will have phases that depend on each side of the lattice, that depend on the potential vector that you include, for example, for the gauge you choose. And then, can you still use this K1 and K2? Does it make sense in this case?
Yeah, it does, because you are using linear response theory, so you work with functions that are original function, you know. And so
We can discuss that.
you work in the limit of linear response.
Any further questions? Yeah, Shannon.
You briefly mentioned graphene.
Graphene.
So what is
graphene especially? What makes it
Well, there
special?
has been a lot of developments on graphene. In fact, one of the main developments related to this field was the fact that this is a very simple system and this has been used as a, let's say, a table practice. Well, what it's special is first the fact that it has naturally the Dirac cones, and what many theorists have done is to imagine modification of graphene and to study which result there will be. So what they do is, for instance, they introduce higher spin orbit interaction in graphene. Obviously, graphene, the spin orbit interaction is very small, but the first prediction of what is called the spin quantum Hall effect is done by assuming that in a network like graphene there is strong spin orbit interaction, and they showed how introducing this high spin orbit interaction would be equivalent to having an effective magnetic field on each non-equivalent network of atoms. There are two non-equivalent atoms in graphene. So you have two different two network hexagonal atoms, and the introduction of a high spin orbit interaction is equivalent to have for each of the networks an opposite magnetic field, and it gives rise to the quantum Hall spin, because it gives rise to two edge currents, each one in one direction, each one one spin. This is exactly what means the quantum spin Hall effect. Obviously, it was a theoretical theorem that was impossible to prove in graphene, but then all the people had the idea of trying to look for this state in systems with very high spin orbit coupling, like HGT, and it was immediately after this theoretical development. So it has played most of the topological ideas have been first tested in some kind of modified graphene and then extended, and the experimenters have thought about this and found the effect in other systems. Okay.
Further questions? I'd like to raise one issue. We always get the question that you're generating understanding on systems that you've prepared yourself, but what are the applications of all this? And now I thought solid-state physicists were much more practical than high-energy physicists.
Well,
but is it clear yet where this will be?
Well, you see that the first system that was studied is the first quantum Hall effect system. Has had a very clear application. Now it is a standard resistance. It's a very clear thing. Then there are lots of hopes, let's say, on these systems of topologically protected interfaces are thought to be able to create some kind of exotic devices in which some kind of excitation would have specific quantum properties to be used in quantum computing and things like this. So there are people studying the interface between a superconductor and a topological insulator, and there are lots of work being done. But most of them, the main idea is the idea that because these systems are topologically protected, the quantum system that we are able to develop from them should be very robust. So they would be not so sensitive to disorder. There are a lot of people working on the application of this system to quantum computing. So there are a lot of work done.
Okay, if there's no further urgent questions, I think we should stop here. Thanks for coming.